All right. Hey, let's talk a little bit about unbalanced forces. Sorry, let's talk again about a little bit about unbalanced forces. And today we're going to talk about a big one. Okay, we're going to spend a decent amount of time talking about this category, and that is the force of friction, one that we are all familiar with, but now we're actually going to measure it and put some other terms to it. Okay, first one, the static friction force. Okay, so the static friction force is going to be a force that exists between two surfaces while they're not moving. All right, that's kind of a big note to have there, is that, your chair on the floor, your car parked on a hill, etc. It is friction that exists between two static surfaces. And it's exerted, like I said, when there's no relative movement, just by you standing there. There is friction between you and the ground. Otherwise, you would be sliding all over the place. It is what's going to hold objects in place. The next kind of friction is the kinetic friction force. So that is the force exerted on one surface by the other when the surfaces are in relative motion. Okay, once again, you are familiar the differences between these two from a practical standpoint, but now we're going to talk about what the actual differences are as they go. So we all know that an object that's at rest tends to stay at rest, but an object in motion tends to stay in motion. So the two friction types of friction are different there. So a model that we're going to be using for our frictional forces is we are going to assume that the only thing that matters is what kind of surface is on the other kind of surface. Okay, rubber on concrete, wood on metal, plastic on glass. Those kind of things. Two surfaces rubbing against each other. In reality, the surface area of the two also is important. Okay, the more surface that is in contact, then the more potential friction there could be, but we're not going to worry about that. We're just going to worry about what the surfaces are. And here's our formula. All right, that looks pretty intense, but there we'll be okay with it. That F sub F is going to be the frictional force, is what that stands for. All right, so the frictional force is going to equal, and that is the Greek letter mu. Okay, that is how they denote the force of the coefficient of friction, I should say, is what that stands for. And then, so it's the coefficient of friction times the normal force there. All right. The coefficient of friction is a unitless label. It's going to be something that is given to you, or we have to figure out based on some simple geometry, but it's not something that you have to memorize or anything like that. And then F sub n is the normal force. You guys remember that? That is the mass times 9.8. Here's an example of coefficients of friction. I said the closer to 1, the more friction that there is. The further away from the closer to 0, the less friction that there is. All right, so you'll never see a frictional force of 1 or one that's below 0. It's always between 0 and 1 there. All right. Here's our example that we have here. Now I don't have a board today to go through, but that's okay. So Ethan Bush's 25 kilogram wooden crate full of pirate gold across a wooden floor at a constant speed of 1.0 meters per second. How much force is Ethan exerting on the crate? Okay, so to do this, we would take, so he's not accelerating the crate at all. So the force that he's exerting is exactly the force needed to overcome friction. So we would take 25 times 9.8. And we would use, let's see, 25 times 9.8. So it's roughly 250. Then we'll use that wood on wood for 0.5. And we get an answer of 49 newtons. All right. So hey, there is frictional force today. Go ahead and try your best on today's assignment.